What's the first principle of differentiation? So we basically know that if you're given y is equal to, for example, 3x, let's take it to be 3x plus 1. You know that when you're dealing with the dy dx of that function or the derivative is basically going to be equal to 3. If we add 3x squared and then let's say plus 2x, right? So you expect that the derivative in such a case, we understand that you will need to multiply the power by the coefficient, reduce the power by 1. So 3 times 2 is 6x, reduce the power by 1, it becomes just 1. And then all the same x to the power 1, 1 times 2 is a 2, reduce the power by 1 becomes 1 minus 1 becomes 0, x to the power 0 is just a 1. Okay, so you therefore have 6x plus 2 as a solution. Now according to first principle, the first principle is based on the idea that the derivative, which we call the derivative function, can help you determine the gradient at a given point. Now, if you remember the way you used to calculate the gradient of a linear function or a straight line, if you're given two coordinates of a line, right? Let's say these are make up a certain line like that. You're able to find the steepness of the gradient of a line by saying your gradient denoted as m is the change in y divided by the change in what? In x. So change in y, your y26 minus 4 from the other one, taking that as our y2 and this is a y1, this is our x1 and as x2, as well as for the x it will be 3 minus 2. You get to observe that your solution will be 2. So that is our gradient. Now we can use this basic idea to basically differentiate the function that we have. They are using what we are calling now the first principle. So the basic idea is to take the function to be the y coordinate. Okay, so for the first coordinate we're going to have x comma y. Now y is equal to that, so we have 3x squared plus 2x as our first coordinate. Now for the other coordinate, which is where the most important part of this principle is, you'd have to introduce now x plus h. So you are saying, okay, if we have, of course using the example of a straight line, if this is your x or y plane and then you have a line, the basic idea is this. Okay, so we have an original point there. Now we are now trying to come up with a certain coordinate, with another coordinate, where we are saying if this is x, okay, well, what will happen as we increase by h to the right? So that coordinate, we are using h to denote the magnitude by which you've moved to the right or the left. So let's say it will be there. Now we understand that for you to find the y coordinate or the y value of a function, you just need to plug in the value of x. Now if we are taking our value of x to be x plus h, that would mean that we need to substitute in that original part of a function. Where there is x, we put x plus h. So we're going to have 3, then x plus h squared plus, now we have 2x, so where there is x again, we put x plus h. The moment you just get that, no matter what you're going to have, it will all be simple for you. So therefore, our dy dx, in other terms, in some textbooks will give you the formula as the function of x plus h minus the original function divided by what? Divided by h. So the basic idea is this: we're just trying to focus on the change in y divided by the change in x. Now note that for the second part, the change, the y2 is basically the function. Of course we know that y represents f of x, so at every part of where we've got the function, where we've got x, we've put x plus h. So that is as good as saying f of x plus h, and then f of x is the original part. So in other terms, all we are doing is this. Okay, we're just subtracting them. So I'm subtracting this y2, so 3x plus h squared plus 2x plus h, and then minus the first part, which is 3x squared plus 2x. And then of course for a denominator as well, we have x plus h minus x, which will just give us h as a difference. Okay, so at this point we are able to expand. So if we expand what is in the brackets there, you can agree we have x squared plus 2hx plus h squared, and then we have, if you multiply there, we have x plus h, 2 times x, 2x plus 2h, minus, if you distribute the negative, what is there, we're going to have 3x squared minus 2x. Okay, so to just make sure that we speed up on things here, we can actually multiply by this 3 to whatever is inside there. So there, that one will become 3, that one will become 3 times 2 becomes 6, that one will just become 3. So that I can just remove the 3 there. Don't forget on the bottom we have what? We are dividing by h. Okay, so with that understanding, we're able to simplify this. So our dy dx is equal to, so we have 3x squared for the first part plus 6hx plus 3h squared, and then we have plus 2x plus 2h, and then what we're subtracting is we're subtracting minus 3x squared and then minus 2x. So that is able to cancel out with that, and then the negative 3x squared is able to subtract that as well, and then we are dividing by h, which is on the bottom. So you can clearly see that h is common, so you can easily factorize it on the top part. So if you remove h, you remain with 6x plus 3h plus 2, and then the h on the bottom can now divide. Okay, so what is standing out is you have 6x plus 3h plus 2. Now for you to find the solution, a full answer, what you basically get to do is you need to, we are dealing with the limiters as x approaches, sorry, as h approaches 0. That would mean that if we apply that limit on 6x plus 3h plus 2, it means where there is h, you put what? 0. So that will go away. So your answer remains 6x plus 2, which matches up with the first part there. Okay, so let's proceed and look at a few other practice questions on the same, where we'll look at fractions as well. And let's talk about the formula of differentiation. So the basic idea that we've looked at so far is we've looked at the first principle. Of course, I understand that you've done this before, okay, but I still want to break it down. So we have 3x squared plus 2x, right? So we understand that the dy dx, which of course represents the derivative of that function, is going to be 6x plus 2, where I've emphasized you need to multiply the power with coefficient, reduce the power by 1 and all that. Now we need to introduce it now in the form of a formula. That's a formula that we are using, but you need to understand exactly what's going on. So what we're trying to say is if y is equal to a coefficient of n, right? Let me put it this way. If you've got y is equal to a x raised to a certain power n, okay? If you are trying to differentiate that in respect to x, y in respect to x, it has to be multiply the power with a, so it will be na as a product, and then x raised to the power is supposed to reduce by a 1. So this is the formula for differentiation. Very important for you to understand. Okay, so that's what we've been using. I just needed to mention that, but we can look at I understand that this is easy for you to deal with. These polynomial functions are easy to deal with. Now let me try to look at rational functions, not necessarily rational functions, but maybe radical functions and all. Let's consider guess what we've got a fraction, by the way. 1 over, let's say, 2x. How do you apply that formula? So dy dx, before we actually bring that up, you need you to understand that if you've got two, maybe I can start with something as simple as 1 over x. So if you've got 1 over x, if you take it to the numerator, that's as good as saying x. So on the bottom there is raised to the power 1. If it goes to the numerator, it becomes the power -1. That's very important. So at that point, you realize or you understand that if you need to apply the power rule, what you do is as follows. Okay, so this is going to be your dy dx is going to be equal to, the coefficient there is a 1, so -1 times 1 will give us -1, and then x, you need to reduce it by 1. The power is supposed to reduce by 1, so it becomes -x raised to the power -2, which you can gradually take on the bottom by becoming -1 over x to the power 2. That's as good as that. So that's what you have applying the power rule. So all the same, even if you had, let's say, the power 2 and all, if it goes to the top part, it becomes -2, and then it becomes -2x, and then the power reduces by 1, it becomes -3. You can take it on the bottom if you want, so that you have -2x to the power 3. Okay, so now what changes if we are to introduce, let's say, a 2 there, so that this is now 1 over 2 x squared. So all the same, the fraction will remain, the number will remain on the bottom, but you need to take the x back to the numerator so that it becomes a negative power. Now the coefficient in this case becomes half. So -2 multiplied by half, and then x reduced by, the power is supposed to reduce by 1, so it will be -2 minus 1. So this and that will divide, you have a -1, and then you have x to the power -3, so which is as good as -x. You take x on the bottom, so it will be -1 over x to the power 3. Okay, so that's the interesting part about this. So that's basically how you can apply the power rule, which we are coding the formula to just basically perform basic differentiation. Okay, so as the name entails, product rule, this is where we talk about the product of two functions. Okay, so let's say in a case where you've got your y, it's a product of two functions. Let's say you have x plus 2, and then multiply by x squared. Maybe let me put it this way: 2x, 2x squared, even plus a 1. So if you look at this from that point, of course this is easy because you are still able to multiply them and all that, but the basic idea is you can use a product rule in a simpler way to avoid using the power rule, because it take a lot of your time. So when you've got product of functions, we use a product rule to basically help us to determine the derivative. So the way it works is as follows: if you have your dy dx, you want to determine your dy dx if you've got a product of two functions. Okay, so you're going to look at it from this way. You can determine the derivative of the first part, which in this case, you know that if you differentiate what is in the brackets there, you're going to just have a 1. To make it interesting, I can put a 4x there. So if you differentiate that, you're just going to get a 4. Multiply by the original part of the other side. So you have 2x squared maintained plus 1. And then all the same, we'll do the opposite. This time around, we'll differentiate the other part. Okay? So to make it interesting, again, I'll remove that so that I put a 3, so that you can see what's going on here. So if we differentiate what it is on in that other bracket, you are going to get 6x. Open the brackets. We need to multiply by the original part of the other part, which is 4x plus 2. So this becomes, if we try to open this bracket, 4 times what is inside there, you're going to have 8x squared plus 4 plus 4. 6 times 4 is 24x squared. 6x times 2 becomes 12x. If we are to collect the like terms there, 24 plus 8 basically becomes 32. And then we have a 12x there plus a 4. So this becomes the derivative. Now, going back to the initial step, which is very important, what we have is, first of all, getting the derivative of the first part, multiplying by the original part of the other part, which now, of course, I've made a mistake because of the correction I made there. So this changed to 3, by the way, so that was supposed to become a 3. So that if you multiply, it becomes a 12. Now 12 plus 24 becomes 36. Okay, yeah, all the same. So taking this to be u, taking that to be v, the product rule is as simple as the derivative. When you've got a product of two functions, just get the derivative of the first part, which we'll call u prime, multiply by the other one v, and then add. Now if you look at the 6x, 6x is as a result of differentiating v, so we'll take that as v prime, and then multiply by the original other side. So you understand that addition is commutative. It doesn't matter what you start with. So even if you start with a derivative of the other one, it is still the same. Okay, you don't have to stress about it. But basically, this is the basic idea about the product rule. For your practice, feel free to just pause the video and just try out this. Let's set the power one. This is derivative so simple. This is derivative so simple. You can even deal, but I want you to apply the product rule instead of working with the power rule. So all the same, dy dx, just to help you remember the formula, there are no restrictions. Addition is basically commutative. Okay, so but I like it this way without using the formula. The product rule tells me I just need to differentiate the first part. So 2 times 3 will give me 6, so I have 6x. I need to multiply this by the original other part as it is, and then plus. So I need now to differentiate this other part. I don't know why I'm coming up with such equations which are giving me the same result. Okay, it will be different anyway. 3 times 2 will be a 6. Now the power reduced by 1, it becomes x squared. We multiply by the original other part, which is 3x squared. That's the basic idea. Okay, so I have 6x. Let me just multiply. 6x multiplied by what is there? 6 times 2 is 12. X times x to the power 3, x to the power 4, plus 1 times 6x is that 6x. And then the other part is 18. 3 times, that is 6 by 3. And then x squared times x squared is x to the power 4. 18 plus 12, that's 30, plus 6x. So that's how as simple as this is the way it will come out simply. Okay, so later on, after you've looked at the exponential functions, it's going to become more interesting because you can actually have a product of a quadratic function like 2x multiplied by exponential raised to the power 2x. That's also a product. You can also have logs as well. The same concept will still apply. Okay, you have log x squared multiplied by a certain other function like an exponential and all. So you'd have to apply the same principle. Multiply the original part by the derivative of the other. Okay, I'll give you an example of this one, just in case you're curious. So I'll differentiate the first part. The derivative of 2x is just a 2. And then I'll multiply by the original other part. and then this other one now I need to start with by the derivative of e to the power 2x. So the derivative of an exponential function is differentiate what the power is there. Okay, differentiate what the power is. So the power in this case, if you differentiate 2x, which is a 2, so multiply that, so it will be 2e to the power 2x. The power doesn't change for an exponential function, so our derivative is 2e to the power 2x. That's why if you've got e to the power x, the derivative is 2e to the power x, because the derivative of x is a 1. 1 multiplied by that, nothing will change. Okay, and then we'll multiply by the original first part. Okay, so you have 2e to the power 2x plus, and then here if you multiply, you've got a 4x e to the power 2x. You can end there as a solution, but most of the times I prefer to factorize e to the power 2x, which is common, and then remain with what in the brackets. That the first part will remain with a 2, the other part will remain with a 4x. So again, 2 is still common, you can still factorize it out, so that you basically remain with 2e to the power 2x is common. There I remain with the 1 plus 2x. Basically that's what you have. Okay, so this is what we're getting now. The product rule, we are done. Let's move and look at the quotient rule. Okay, so talking about the quotient rule, just as we've talked about the product rule, this as well deals with where you've got quotients, right? Where you're dividing. So in a case where you've got y is equal to u over v. Okay, so here now the formula tells us that if you want to determine y prime or dy dx, which are the same, the formula is as follows. You need to start with the denominator, multiply by the derivative of the numerator minus the opposite, which of course we expect to be u multiplied by v prime divided by v squared. This one is very important. It's very important. One way that I help myself remember is whatever I have on the denominator should come finished, and then multiply by the derivative of the other, and then subtract with the opposite, and then divide by the denominator squared. That's easy to remember, right? Okay, let's try to look at an example. So in a case where you have y is equal to x squared over x plus 2, you want to differentiate that. So I've said it's as simple as starting with what? The denominator. The denominator in this case is x plus 2. So you have x plus 2, right? Multiply by the derivative of the other part, which of course is the numerator. So that's going to give us 2x minus the opposite. So don't forget we started with the denominator, so we're going to start with the numerator, which is x squared, multiply by the derivative of what is on the denominator, which is a 1. X plus 2 differentiated is a 1 over the denominator squared. This is equal to, if you need to multiply that, don't forget 2x is multiplying with whatever is there, so you're going to have 2x squared for the first part, and then 4x, and then minus x squared over x plus 2 squared. So these can subtract. 2x squared minus x squared is just x squared plus 4x over x plus 2 squared. On the top part, if you want, you can factorize, so that you have what? X and then x plus 4. So it's not worth it, we can leave it there. Okay, so basically that's a basic idea on what you basically are required to do on how to apply this. Others would prefer to remember the formula and all, and then start finding u prime, but I feel it's basically more direct. Where you think of it is, I'll start with the denominator, multiply by the derivative of the numerator, okay, and then subtract the opposite divided by the denominator squared. That's the basic quotient rule that you need to remember. Okay, feel free to pause the video and just try out this one, where you have your y being equal to 2x plus 1 and then divided by 3x plus 1. That's one. Is very simple. Okay, so I will now apply the formula just to make sure that you can, if there are people interested, they can also take note of it. So looking at what I've written there, my u is what is on top, so my u therefore becomes equal to 2x plus 1. The u prime is the derivative, so it's as 2, and then for v is equal to 3x plus 1. V prime becomes 3. So I'm getting these after differentiating. So your dy dx now becomes, according to the formula I said, start with the denominator. So your dy dx is therefore equal to your v, which is the denominator, multiplied by the numerator's derivative minus the opposite, which is u v prime, over v squared, which is the denominator, of course. So our v is 3x plus 1, and then our derivative of u is a 2, minus, for u we have 2x plus 1. Now you have to be very careful with the brackets. Our v prime is a 3, divided by v squared, which is 3x plus 1 for the denominator squared. So you're able to simplify, multiply the 2 with whatever is there, multiply the 3 with whatever is there, and then subtract. So we have 6x for the first part plus 2, and then we have minus, we've got a 3 there, so I'll open the bracket, 3 times 2x, that is 6x plus 3 over 3x plus 1 squared. Of course, the top part you expect 6x minus 6x will give us 0, and then you have got a 2 minus 3, which is a negative 1, over 3x plus 1 squared. That's how simple this is. Alright, so basically that's it about the quotient rule. Let's move on and talk about the chain rule. Let me introduce the basic idea of chain rule. Okay, so chain rule basically focuses on the idea where you've got, I usually like thinking of it in a case where you've got like brackets. Let's say y is equal to, and then you have 2x squared plus a 1, the power 4. In this case, chain rule is more like a combination of power rule with something new or extra. You understand why it's called a chain rule. So you take your whatever is inside the brackets to be your u, and then the power 4. Okay, so the way we basically get to under this is the u that you have, in this case our u is equal to 2x squared plus a 1, so that can be differentiated. So differentiating that, it's du dx, because we're differentiating u in respect to x. We're going to have what? 4x. And then we can also differentiate the part where we've substituted u, so it's y in respect to u, so it's dy du, and then we have got a 4u, and then the power reduced by 1 to the power 3. Okay, now you've got this and you've got that. So if you try to multiply the two, there's one thing that is going to be interesting: dy du multiplied by du dx. So the du's will cancel out, you remain with dy dx. So in other terms, if you multiply the two, you are going to get an answer. So 4u the power 3 multiplied by 4x, you are going to have 16, and then x, and then u to the power 3. Now pull back your u. Your u is what? Your u is 2x squared plus 1 to the power 3. So that's the result, and this is why it's called a chain rule. It's a chain. Okay, that's the basic idea, using the formula and all that. Now I don't like formulas. I don't like formulas. So now that you know what we're talking about, by the way, don't forget the answer. That's our answer there on the bottom, using what we're calling the chain rule. So the way you can go about directory is as follows. Consider the coefficient that you have there. So this is a case where you only have a coefficient but you don't have another function. If you do have, let's say, where there's 1, if you add maybe 2x squared and then multiply by whatever is there, the formula changes. This is now, it becomes the product of two different functions making up this function. So there you have to apply what we're calling the product rule. So review it, don't forget about it for now. Going back to our question, so the form normal differentiation using the power rule, where you take a 1 to be a coefficient. 4 times 1 is a 4, and then maintain what is in the brackets, and then reduce the power by 1, which is a 3 now, and then multiply by the derivative of what is in the brackets. That's the only thing that you add. Multiply by the derivative of what is in the brackets. The derivative of 2x squared plus 1 becomes 4x. And then if you multiply 4x by 4 outside becomes 16x. Now 2x squared plus 1 remains in the brackets. So you've seen that it's not as complicated as the formula. The formula takes and wastes a lot of time. Okay. So you can actually apply the same idea, the combination of chain rule and product rule, to answer the other part. But let me try to give you other forms of, or other things that would require you to apply the chain rule. So you can have a case where you have the square root of x to the power 3 plus 6. You can also apply the chain rule there to determine the derivative of such a function. So a dy dx becomes, now you understand that the square root is as good as adding it to the power half. Even if you have got the fourth root, you understand that it becomes the power 1 over 4. So it shouldn't be a struggle, you shouldn't be intimidated when you see such an expression. So, I don't know how to differentiate such a function. So I don't know why I've written that, but this is still y. So now the derivative, which is y prime or dy dx, becomes, remember the coefficient there is still a 1. Now let's make it more interesting. Let's assume we had the 4 there, and then we've got the 4. So 4 times half becomes a 2, and then reduce the power by 1. So half minus 1 is just going to be negative half. Basic fractions. Now the thing that we're adding is where we multiply by the derivative of what is in the brackets. The derivative of what is in the brackets, in this case we have 3x to the power 3 plus 6, so it's just going to be 3x squared. This times that gives us 6x squared. What's remaining in the brackets? We've got x to the power 3 plus 6 to the power negative half. We can end there, that's still fine. I like taking it to the denominator so that we have a positive power. So the x to the power 3 plus 6 can go to the denominator, so that is now raised to the power half. Now the power half is as good as putting a square root now. So you look to be more understanding of what you're doing if you express an answer like that. So that's where you end. Now for the sake of your practice, I want you to try out this one. Y is equal to 1 over, I know students, when you meet questions that you've never solved, you feel like you can't answer it, but all the same, you know that if you've got something on the denominator part, you can just take it to the numerator, right, and then raise it. The sign changes, it becomes negative. So all the same, there's a 1 there. If you multiply, your dy dx becomes negative 3. Maintain what is in the brackets, reduce the power by 1, it becomes negative 4. Multiply by the derivative of what is in the brackets, which is 2x. Negative 3 by that, it gives us negative 6x. Maintaining what is in the brackets, we can directly take it on the bottom so that the power becomes positive. That's your answer there. And the other thing that I want to mention is, I know we'll talk about these later on in detail, how to handle them and deal with them, but for now just know that the derivative of sine x dy dx is just as good as cosine of x. I want you to know that. The derivative of cosine on the other hand gives us negative sine of x. So we'll look at more complicated stuff later on, the derivative of tan and all, but there's an association of these two what you're dealing with, the chain rule. So the basic idea behind the derivative of this is you can let whatever is there be your u, so y is equal to u, and then your u becomes equal to the function itself, sine of x. Now if you say dy du, you notice that in this case your u just becomes I think this is wrong. I've done it in a wrong way. Instead we can say it's this part which becomes u, so sine u, and then your u becomes equal to x. So dy du is, now the derivative of what? Of sine is cosine, so you have cosine of u, and then the derivative du dx there becomes just equal to 1. So 1 times cosine of u is just cosine of u. Now your u is equal to what? X. So that's the answer in such a case. Now why am I showing you this? I'm showing you this because it becomes more interesting if we add 2x there. If we add 2x. So if we add 2x, this still maintains, it still maintains to be cosine of u, but this part becomes u is equal to 2x. So the du dx becomes 2. So if you multiply, you have 2 cosine, and then the u is still 2x. Okay. So that's the basic idea there. We'll talk about trigonometric differentiation later on in detail. Now just to end this, how do you handle a question where you've the product rule being combined? Copying the question again, x squared multiplied by 2x squared plus 1 raised to the power 4. So we have a product rule. So I said the product rule, maintain the first part as it is, or differentiate it if you want, but I'll maintain it in this. I'll differentiate it in this case. The derivative of x squared is 2x, and then the other part should be maintained as it is. So maintain 2x squared plus 1 to the power 4. Now for the next part, as we add, we need to differentiate the other one as well. So now how do you differentiate this? Now you know this is where now the chain rule comes in to differentiate this. So I said consider it as it is. The coefficient there is a 1, so you have 4. Maintain what is in the brackets, reduce the power by 1, it becomes the power 3, and then multiply by the derivative of what is in the brackets. So the derivative of 2x squared plus 1 is just as good as 4x, and then multiply by the original other part, which is x squared. I hope you're not confused. This becomes 2x squared plus 1 to the power 4 plus, and then this multiplied by that just gives us 16x. Maintaining what is in the brackets, we have 2x squared plus 1 to the power 3. Now don't forget that what this is multiplying by the x squared. Okay, so if you multiply with what is in the brackets there, the x squared can just be part of the 16x, so it becomes the power 3. I think that is better off. So you can end there, but I prefer simplifying it further, where you can factor out the 2x since it's common, and then the other part that is common is the 2x squared plus 1. Now to what power? Here we've got a power 4, here we've got the power 3, so we'll get the smallest power, which is 3. So now in the brackets you remain with, for the first part, 2x has been taken there, since it's the power 4, here you've got the power 3, you remain with a single 2x squared plus what? Plus a 1. And then the other part plus if you factor out the 2 from 16, you remain with 8. Factor out x, you remain with x squared. Okay, the entire part has been taken to the power 3, but I think these are like terms as well. So 8 plus 2 gives us 10. So you remain with 10x squared plus, I think, did we have a 2 or something? Why am I forgetting what was there? Oh, we had the 1. Yeah, so that's our final answer. This is interesting. This is just interesting. I like it. So that's it about the chain rule. Let's talk about the sum and difference rules, of which I just feel like they're basically okay for me. I feel like they're just like part of what we do. But the basic idea is if you have y being equal to the summation of two different functions, f of x plus g of x, the derivative of y, which we'll call y prime, is the same as derivative of the individual function itself, in this case f of x, plus the derivative again of g of x. Okay, so what this means is the derivative of the entire part is equal to the derivative of the individual, the summation of the derivative of the two parts. So the basic idea is if you are adding two functions and then you decide to differentiate y as a whole, it's basically the same as differentiating these individual functions and then just getting to add them. Okay, maybe to make more sense as we look at an example. So if you have y is equal to 3x to the power 4 plus 2x to the power 3, we understand that y prime, in this case, you know how to work out this by the power rule. So it will be 12x to the power 3 plus 6x squared. Now what we are saying, according to the sum rule, the derivative is the same as, since these can be considered to be separate functions, y prime is also equal to the derivative of 3x to the power 4 plus the derivative of 2x to the power 3. So even if you do them separate and come to add them, you still get the same result. That's the basic idea behind the sum and the difference rule. Giving you one more example, which maybe will make more sense, but in this case you can see the necessity of doing that. So if you've got that and equal to cos 2x, so this is a function. In this case our overall function is y, but this can be taken to be a separate function, that can be taken to be a separate function. So sum rule, or even if you have a negative there, tells us that you can basically get the y derivative by, first of all, take this part, differentiate separately, take this part, differentiate separately, and come to add their results. You have your derivative. That's what the rule tells us. So if you have a negative as well, you can put a negative there. So we can get the first part, the derivative of x squared e to the power 2. Now you do understand that here we've got a product of two different functions. You can apply the product rule. And what's a product rule? Try to remember it. Okay, so the product rule, we apply addition there. So addition is commutative. It doesn't matter what you start with. In this case, I'll start by the derivative of the first part, which is 2x, and then I'll multiply by the original other part. I'll maintain e to the power 2, and then plus, and then now I'll differentiate e to the power 2. So let me make it e to the power 2x to make it interesting. So the derivative of e to the power 2x becomes what does the derivative become? The derivative of the power, which is 2x, is just a 2. So I have a 2 multiplying the e to the power 2x itself. We already talked about derivative of exponentials. And then what else do we have? And then we can have let me put this, we can have something like multiplying. Now we have to multiply by the original other part, which is the first part we started with, x squared. That's the product rule. So you have 2x e to the power 2x plus 2e to the power 2x x squared. Okay, so that's our first part. Now you can also get the cos 2x as well, and then also differentiate it. Now you understand that cos 2x is a basic trigonometric derivative. So here we apply the chain rule. So the derivative of cosine is what? Is negative sine. So negative sine, maintain what is attached to it, and then multiply by the derivative of this part. So the derivative of 2x is just a 2, so the answer becomes negative 2 sine 2x. Okay, so to get your final result for y prime, it will be the summation of the two answers. So you have 2x e to the power 2x plus, so I can say 2x squared e 2x minus 2 sine 2x. So that's the idea about the sum and the difference rule. It tells you you don't have to worry about splitting them. You can split them and then come to add their derivatives together to get the overall derivative of y. Now, for your practice, I want you to look at this and just differentiate this. Plus natural log of x and then minus x squared y. So you've got three parts that you can split into individual functions. You know the square root is the same as the power half. So after you've learned about the derivatives of the logarithms and then also implicit differentiation, be able to answer this question. Write it down. You should be able to answer this question after watching the entire video. Okay, let's talk about the derivatives of exponentials. So I like beginning with a simple part. Okay, so begin with where we've got the base of e to the power x. Okay, a bit so you realize that the derivative of that is basically the same. Okay, so don't ask questions for now. So the derivative of that is just e to the power x. So the basic idea is if you've got an exponential with a base of e, so let's say e to the power 2x. I think this will now help you understand what we're trying to do here. So the derivative of e to the power 2x is the base itself, or maintain the original part itself, e to the power 2x as it is. Now multiply by the derivative of the power. Now if you look at the power is 2x. What's the derivative of 2x? You know it's 2, right? So your answer becomes 2e to the power 2x. Alright. So now, applying the same rule to the first part, you understand that the power of x is what? Is a 1. So if you multiply 1 by e to the power x, that's why we are maintaining the same result. Okay. So if you've got derivative, I want you to find the derivative of, let's say, e to the power x squared. Feel free to pause the video and just try it out. So what you might expect there is, ask yourself again, what's the derivative of a power? What's the derivative of a power? The power is x squared. That's the derivative of that. That's 2x. So the answer becomes 2x. Now multiply by the original part, which is e to the power x squared. Now one thing that is interesting about exponentials is the power does not change. Okay, very important. So that's it about the where we've got the base of e. Now what we can now look at is where we've got different bases. Let's say you have y is equal to 2 to the power, let's say, x. What's the answer there? How do you differentiate that? So now the basic rule that you need to understand is whenever you're dealing with the derivatives of exponentials, dy dx, is given as coming up with a general formula. Let's say you've got y is equal to, and then your base is a, and then raise the power x, for example. In such a case, the general, or maybe let me put u at the power u, right? You've got at the power u. The basic general rule that we've seen is maintain first of all what you have at the power u, and then we've seen that we also need to multiply by the derivative of the power, and then we also need to multiply by the natural log of what? The base a. Okay, so what that means is, for what we have, our y prime or our dy dx is going to be maintain first of all what we have, and then multiply by the derivative of x, which is just a 1 in this case, and then natural log of 2. So therefore our answer reduces to 2x natural log of 2. Okay, let's look at some more examples. So what if you have a base of 4 and then raise the power to x plus x squared? What's the answer there? Feel free to pause the video. So our y prime is going to be, so for the first part you can see that that's an exponential, right? So focusing on this, what's its derivative? So the derivative is going to be maintain it first of all as it is, and then multiply by the derivative of a power, which in this case our power is 2x. The derivative there is what? Is a 2, and then multiply by the natural log of a base. So our base is 4, so natural log of 4. Now plus, what's the derivative of x squared? We understand there that's basic power rule, so it will be 2x. So if you want to simplify or put an answer in a simpler way, I like starting with what? Just a constant, so you can have 2 and then 4 the power 2x, and then natural log of 4 plus 2x. So that becomes your answer as a derivative. Now at this point I know most of you are wondering why for where we had different base of it was a bit different. So where we had the base of e, the power 2x, we are actually applying the same concept. So remember that we said that here the derivative is going to be maintain it as it is, multiply by the derivative of the power, which is just a 2. Now why are we ignoring the part for the natural log, since we are saying it's supposed to be a natural log of the base? So we understand that natural log basically means, in case you didn't know, natural log means log with a base of e. So if you have got e there, then you know that it's equal to 1. So basically if you've done logs, log of the same base and then you've got the same number there, that is equal to 1. So natural log of e, that's an inverse, so that is equal to 1. So it's not necessary for us to show that part when we have a base of e. That's why we're just trying to ignore it and just saying just multiply by the derivative of the power to the original part of the function to get the derivative of an exponential with a base of e. Okay, so for your practice, make sure you're able to answer this question. Try this one out. So 3x squared plus e 2e to the power 4x plus 2x to the power 4. So feel free to pause the video and just try this one out. Let's talk about the derivatives of logarithms. So I'll begin with the natural log before we look at the normal logarithms with different bases. Okay, so what's the derivative of natural log of x? So the derivative of natural log of x is basically equal to 1 over x. Okay, so why is it so? So the general formula, maybe let me give you another example to just trick you. D of x. What if we've said natural log of x squared? What do we expect to be the answer there? So the answer is 2x over x squared, which can simplify to 2 over x. So you're trying to get the idea there. So the basic idea behind the differentiation of natural log or logarithms is that if you have natural log of u, the derivative there, the derivative of that is going to be u prime divided by u itself, okay, multiplied by natural log of e. Now you understand that we've already established to say the natural log of e is equal to 1. Why am I saying natural log of e? It's because I know that natural log has got a base of e there. It's a log with a base of e. Okay, so it's very easy. So each time you have a natural log, you work it out like that. Now let's try to look at a more advanced example, or let's try to look at more practice questions to just ensure that we're able to remember. So how about y is equal to natural log of x squared? Feel free to just pause the video and try that one out. So obviously we expect that y prime as well, it will be the derivative of this part, which in this case is 2x over x squared. I think we've already talked about this one, so it's 2 over x. Okay, that's repetition. What if we say natural log of 3x squared plus 2? So all the same, what's the derivative of 3x squared plus 2? So the derivative of that is what? So it's going to be 6x now over the actual function itself, 3x squared plus 2. That's the way you differentiate logarithms. I can give you another example. What if we say we have natural log of 7x plus 1? So the derivative there is going to be what? Derivative is going to be 7. We maintain the original function, 7x plus 1. That's the derivative. We can go on to just make it more interesting. How about natural log of, say sine x? What do you expect? So y prime, so ask yourself, what's the derivative of what is in the brackets? The derivative of sine of x is cosine of x. Now we maintain the actual part, which is sine of x. It's u prime divided by u. So our u in this case is equal to sine of x, and then our u prime, the derivative of sine of x is cosine of x. So it's cosine of x over sine of x. Now we understand that that is equal to cot of x. So that's the answer. So by the way, this is coming from trigonometry identities. Okay, so don't worry much about it if you don't know. We can go on. Just before we look at the logarithms, with different bases other than e, what of a case where we have natural log of, maybe for a practice, try out where we have tan of x. So if you have tan of x, all the same, the derivative there is expected to be what? So the derivative of tan of x is sec squared of x over the original, which is tan of x. That's your answer. What about the case where we have our y being equal to the natural log of the fourth root of x? How do you handle such a question? So you know that you can express that in terms of natural log. The fourth root is the same as x to the power 1 over 4. Now from logs, from basic logarithms, you understand that if you have log of 2 and then x to the power 4, we know that the power of what is attached to the log can become there, the coefficient, so that you have 4 log 2 of x. So the same concept applies to logarithms. The 1 over 4, which is the power of x, can become the coefficient, so that you have 1 over 4 and then natural log of x. So whenever you're trying to differentiate something with a constant, what basically happens is you basically pull out the constant. Okay, so we have 1 over 4 and then derivative of natural log of x. So that is going to be 1 over 4. And then what's the natural log of x? Now the derivative of natural log of x, we say derivative of x, which we know is a 1 over the function itself. So the answer therefore becomes 1 over 4x as a solution to that question. Just one more. Just one more. What about a case where we have the entire natural log, where you have like the fourth root of the entire natural log of, now let's make it x squared to just make it interesting. What do you do in such a case? So what this means is this is equal to the entire natural log of the entire function raised to the power 4. That's what it means. So whenever you have any function in brackets raised to a certain power, this is where you apply the chain rule. You can't just bring the 4 here, it's different. But we know that the 2 that is inside can become the coefficient of natural log, but the 4 which is applying to the entire function can never become the coefficient there. Okay, so we understand from chain rule to say you can rate whatever is in the brackets to be your u. So our u is equal to natural log of x squared. Okay, and then what else do we know? Now we know that now our y will become, if what is in the brackets is u, then we're going to have u to the power 4. So we can differentiate these two parts. So du dx. So what's the derivative of natural log of x squared? So we said differentiate this part, which is 2x, divided by the original part, which is x squared. This reduces to 2 over x. And then for the other part, you differentiate dy du. That is differentiating y in respect to u. So it will be 4u and the power reduced by 1 becomes 3. So we understand that the chain rule tells us you need to multiply these two parts. So we have 2 over x multiplied by 4u to the power 3. Now while there is u, we can pull back what we had, natural log of x squared raised to the power now 3. So you can simplify that by combining 4 times 2, which is 8. So you have 8 over x, open the brackets, natural log of x squared to the power 3. So that becomes your solution. Okay. Now let's maybe for practice try out this one, where you have the natural log and then let's say natural log of what? Yeah, the natural log, and then we can say the third root of x squared. Just feel free to pause the video and just try this one out and see what you're going to get. Okay, so let's look at the basic logs now. What about a case where you have a different base, where you have log 2 for example, and then x? What's the derivative of such a function? So y prime becomes, so I said get the derivative of what is attached to the log. So in this case the derivative there becomes what? So the derivative is just 1. And then I said maintain the function is x, this part again x, and then multiply by natural log of a base, so natural log of 2. So I did emphasize to say on the part where we add the natural log, let's say natural log of x. Here we add only 1 over x because we understand that natural log of e, because when you've got the natural log, the base is e. So that is equal to, this part is equal to 1. So it's not necessary for us to show it. And hence, that's why even if you have x squared, on top you have 2x, and then on the bottom you have x squared. This part is still equal to a 1. Okay, so let's look at more questions. What about a case where our y is equal to log 3 base 3 and then 2x squared minus 1? What do we expect there? So our y prime is expected to be, so if you look at what is in the brackets, what's the derivative there? So the derivative that we expect is 4x divided by the entire function itself, which is 2x squared minus 1. Now, not only is that the answer, you need now to add the natural log of the base, which is 3. So that becomes your answer, 4x over 2x squared minus 1 multiplied by the natural log of 3. Okay. Consider a case where you have y being equal to log of 8, and then you have x minus x to the power 6. What do you expect there? So y prime becomes, what's the derivative of what is in the brackets? So we have 1 minus 6x to the power 5 after differentiating that using the power rule, and then divided by the original part itself, which is x minus x to the power 6. Now we need to add the natural log of the base, which is 8. Okay, I believe this is easy now to remember, applying the fact that whenever you have natural log of, let's say the same one, x minus x to the power 6, it's just the derivative of what is in the brackets, which is 1 minus 6x to the power 5 divided by the original part itself. Now there the difference is you have natural log of e, which is equal to 1, so it's not necessary for us to show it. So in short, the rules are the same. The rules that apply to the log and the logarithms are the same. Okay, what matters is how the final result comes out, which is the difference there, because natural log of e is equal to 1, so not necessary. Okay, with the confidence that I have that you've gotten the idea here, try out log with base 7 and then sine of x. What do you expect there? So here our y becomes, our y prime derivative becomes, what's the derivative of sine of x? So it's cosine of x, and then divided by, maintain the origin of part, which is sine of x. Now add natural log of 7, the natural log of the base. Okay, consider a case where you have y is equal to, what about if the same one, I say log 7 and then I add tan of x? What do you expect? So where you expect that a y prime becomes, the derivative of tan of x is x squared of x, and then divided by the original, which is tan of x, now multiplied by the base, the natural log of the base, which is natural log of 7. Okay, with all the basic ones that we've looked at, what about a case where it becomes more interesting, and then you get to have your y being equal to natural log, and then in the brackets you also have natural log of x? How do you look at that one? This is where you have to, now it becomes interesting. This is where you get to be tested if you've understood what we've been dealing with. So what we've said is, whatever you have in the brackets is supposed to be differentiated. Now you understand that if you pull out that to be your u being equal to the natural log of x, you understand that if you differentiate this part, the derivative of x is what? Is 1. And then maintain the function, so 1 over x. So for what we have in the brackets here, you have 1 over x, now divided by the original part. So the original entire part in the brackets is natural log of x. Okay, so we have 1 over x, So that one is the same as 1 over x multiplied by 1 over natural log of x. Okay, so the answer just becomes 1 over x natural log of x. In short, whatever is on the denominator of the top part just joins the denominator there, so that you just have 1 over x natural log of x. With that simple example, test yourself more. How about a case where you have now natural log and then you have log of 2x squared in the brackets? How do you answer that one? So all the same, first of all, you need to differentiate what is in the brackets. So taking your u to be equal to what is in the brackets, log of 2 and then x squared. So the basic rule there is, what's the derivative of x squared? The derivative there is 2x divided by the function itself, which is x squared, multiplied by natural log of a base. So at least the x can cancel out, so that you just remain with over x squared, 1 will go, so that you just remain with 2 over x. So you have 2 over x natural log of 2. So you have 2 over x natural log of 2. Now divided by what? So I need to be careful I put the equal sign. Divided by what? We need to divide by the original part, which is log base 2 x squared. Okay, now for a part where we've got the natural log, the base is e, so no need of you adding the natural log part. So whatever is on the bottom there joins whatever is on the denominator. So you have 2 over x natural log of 2 multiplied by log of base 2 x squared. Okay, that's what you have as your final result. Anything more? Consider a case where you now have the log base 2 outside and then you have a natural log of 2x inside there. So feel free to pause the video and try this one out. If you can answer this one, then I believe you're very confident of whatever we've talked about. So whatever you have, first of all, differentiate what is in the brackets. Derivative of natural log of 2x, so take it separately. What's the derivative there? So derivative of 2x is 2, and then maintain the function itself on the bottom. So the 2 can divide, so I just have 1 over x, right? Natural log of 2 of x, derivative of 2x is 2, and then on the bottom maintain the function, so you have 1 over x as well in such a case. So 1 over x divided by, maintain the original part there, which is natural log of 2x, and then multiply by the natural log of the base, natural log of 2. So your answer becomes 1 over x natural log of 2 natural log of 2x. So that's our answer for this case. I know most of you are actually way better than me in terms of being able to recall and remember most of these formulas, but I just want to talk about the proof. Yeah, because you know, some of you are able to remember. For example, the derivative of tan of x, you know, some of you know it's x squared x, and then you also know that the derivative of cot of x, you know that it's equal to negative cosec squared x. You know that derivative of sec of x is also equal to sec x multiplied by tan of x. And then you also know the derivative of cosec of x, which even right now I can't remember, but of course it's equal to negative cosec of x multiplied by cot of x. I can't remember all this. I've got issues. The only one I can remember properly is this part. So we are going to look at their proofs from the basic things that we should know. So let us just know that sine of x, the derivative of sine of x is equal to cosine of x. So The way I usually remember this, I trick my brain by remembering this to say, okay, sine is a bit normal. That it is positive, it produces a positive result. Then of course, the opposite is true. The derivative of cosine of x becomes what? It now becomes negative sine of x. Okay, so this is where everything starts from and everything builds up from. So in a case where they give me negative sine of x, I know that sine maintains the sign, so it will be negative cosine of x. I know if I say negative cosine of x, I know that cosine does not maintain the sign, so it will become positive sine of x. But all the same, we'll apply and only use the ones I've written on top there. Okay, let's begin with the derivative of tan of x. So the derivative of tan of x. Now we know that tan of x, so by the way, for you to be watching this video, I believe you've got basic introduction to trigonometry. So you know how to deal with trigonometric identities here. So tan of x is the same as sine x over cosine of x. So if you've not done the identities, watch a video. The link is in the description about the identities, very important as a basic foundation. Okay, so if you've got a division of functions, we've looked at what we call the quotient rule, which I believe you've already done. Okay, so the quotient rule tells us the easiest way of remembering the quotient rule is by beginning with the denominator. Whatever you have on the denominator should start first. So therefore, if this is our y is equal to tan of x, we expect that our y prime is going to be, begin with whatever you have on the denominator. So I have cosine of x. Now multiply by the derivative of the numerator. So the derivative of sine of x, we know it's cosine of x. Now minus, that's a quotient rule. So don't forget that we started with a denominator. So we're going to now start with a numerator, sine of x, and then multiply by the derivative of now the denominator. So we like do the opposite. So the derivative of the denominator in this case, our denominator is cosine of x, so the derivative is going to be negative sine of x, divided by, the quotient rule tells us the square of the denominator, so cos squared of x. So on the next step, y prime becomes, so cosine of x multiplied by cosine of x, that is cosine squared of x, cosine squared of x, minus negative times negative, here we'll get a positive, so positive sine squared of x, and then over cosine squared of x. So some of you already know where this is going, right? So since we've got a denominator of cosine squared x, this is also cosine squared x, we can convert the sine squared x to cosine squared x. So sine squared of x plus cosine squared of x is equal to a 1. I'm not teaching identities, that's an identity. So if I'm to make sine squared the subject, this can go the other side. So sine squared of x becomes 1 minus cosine squared of x. So we can substitute that. So where we have sine squared x, I'll remove it and put 1 minus cosine squared of x. Cosine squared of x. Okay, so our y prime becomes what? So if you distribute the positive, so you end up subtracting cosine squared of x minus the negative cosine squared of x coming from the brackets with a positive 1 over cosine squared of x, which is the denominator. Now this part will subtract, so you remain with 1 over cosine squared of x. 1 over cosine squared of x. So at that point, some of you are already conversant with identities, you know where the answer, what the answer is. So y prime is equal to 1 over cosine squared of x. So I said identities are a prerequisite to this video. So 1 over cosine of x is equal to what? So that is equal to sec of x. So if the denominator is squared, even that will be squared. So therefore our y prime is equal to sec squared of x, which is the thing that you people are able to remember. Okay, so the derivative of tan of x is equal to sec squared of x. So it's not just like people guess, all these are gotten. So we've gotten the first part. I believe you're now able to remember that. So I'll just be taking note of the identities we've come up. So the derivative of tan of x we've already found. It's equal to sec squared of x. Let's look at the other parts now. Let's consider cotangent, the derivative of cotangent. So this is a case where our y is equal to cotangent of x. Now I believe you know your identities. So cotangent is the same as what? 1 over tan of x. Now 1 over tan of x is the same as cosine of x over sine of x. Of course, I've skipped one part. You will know how to perform all these simple mathematical expressions, where if you have 1 over sine of x over cosine of x, it can go back to that. Okay, 1 over a fraction is like the reciprocal, so you just exchange the denominator with the numerator. So that's what we have. Now we can apply again the quotient rule, the same quotient rule that we've looked at. So apply it in this case. Take your u to be your cosine and then the v there. So apply the same thing that we applied to tan, you'll be able to get the answer. Now pause the video and just try that out. Okay, so the basic idea is, again, start with a denominator. So our y prime becomes, our denominator is what? So we are applying the quotient rule, by the way. So our denominator is sine of x. Now multiply by the derivative of the numerator. The derivative of cosine of x is negative sine of x. Now minus, so we started with a denominator, so we're going on to now subtract the numerator. The numerator is cosine of x. Now since we've started with a numerator, we can now multiply by the derivative of the denominator. Now the derivative of the denominator, which is sine of x, the derivative is what? Cosine of x. Divided by, we're supposed to divide by what? The denominator squared. Okay, it's already coming out. So we have negative sine squared of x minus, now this part is going to give us minus what? Cosine squared of x. Now cosine squared of x directly, we know it's the same as 1 minus sine squared of x over sine squared of x. So where is this taking us? So negative sine squared of x minus 1 minus, so if we distribute the negative, we're going to have negative sine squared of x plus sine squared of x, and then minus a 1 over sine squared of x. So I collected the like terms in the derivatory. I know after distributing this negative, this becomes negative and becomes positive. So this will go away, and then what remains? So at this point, what is remaining is negative 1 over sine squared of x, which we now know. I believe we know what 1 over sine of x is, right? So 1 over sine of x, from your basic identities, 1 over sine of x is the same as cosec of x. Okay, so since it is squared, we'll maintain the negative that is there, so it's negative. Now since it's squared, it's going to be negative cosec squared of x. Okay, so, and that is true. So the derivative, can now write that one down as well. The derivative of cotangent of x is basically equal to negative cosecant squared of x. Trust me, I can't remember these, I can't memorize them, but at least I know what I can do. Just if I've got enough time in an exam, I'm able to just compute the answer. And then we can look at the other one. Let's say a case where we have y is equal to secant of x. Now secant of x, you know that this is the same as 1 over what? Cosine of x. Okay, that's an identity. So this is more straightforward and direct. So again, we'll apply the quotient rule. Now the quotient rule tells us to start with a denominator. So we'll start with cosine of x multiplied by the derivative of the numerator. Now the derivative of a constant 1 is a 0 minus, we'll now start with a numerator which is a 1 multiplied by the derivative of the denominator. Now the denominator is cosine of x. The derivative of cosine of x is what? Negative sine of x. Now quotient rule tells us you divide by the square of the denominator, which is cos squared of x. This part is a 0, and then you have now positive sine of x over cosine squared of x. So cosine of squared of x is the same as cosine of x multiplied by cosine of x. You know where that is taking us now. So y prime becomes what? Sine of x over cosine of x is what? So I can take this to be a fraction. So that we have it. Sine of x over cosine of x is tan of x. And then 1 over cosine of x is what? 1 over cosine of x is sec of x. So this is the part now where it gives us that as a result. So the other one that we've obtained is the derivative of sec of x is equal to sec of x itself multiplied by tan of x. Okay. Now feel free to pause the video and try out the other one. So let's say our y, what is remaining? We've dealt with cot, we've dealt with sec, now we're remaining with cosecant. Now y is equal to cosecant of x. Now we know that cosecant is the same as 1 over sine of x. So you can apply the same principle there. So what do we expect? So y prime. So I've said already to say the quotient rule tells us that start with a denominator, sine of x, and then multiply by the derivative of a 1, which is a 0 as well, and then subtract the numerator now, multiply by the derivative of the denominator. So derivative of sine of x is cosine of x, and then over sine squared x. So in the next step I'll continue that. This part is a 0, so we have negative cosine of x over sine squared of x. So sine squared, I can split it again. I can split it, so sine of x multiplied by sine of x, and then I introduce a 1 there. So cosine divided by sine is what? Cosine divided by sine is what? So what is cotangent? Now there's a negative, don't forget. And then 1 over sine of x is what? Cosecant of x. So these are some of the things that help some of you to be able to memorize the formulas. So the derivative of cosecant of x becomes cosecant of x itself. Now there's a negative, don't forget. So negative cosecant of x, and then cotangent of x. I can't easily remember that. Okay. So at this point, including the basic ones that you know, derivative of sine of x is equal to cosine of x. The derivative of cosine of x is negative sine of x. Okay, so you now know how to derive the derivatives of the basic trigonometric functions: tan of x, cotangent of x, cosecant of x, secant of x, sine of x, cosine of x. And these are very useful, as you've seen from the most of the questions that we've looked at. Okay.
Okay, so in this tutorial, we're just going to understand how we go about implicit differentiation.
So what exactly is implicit differentiation? So I believe we know what differentiation is first of all. So if you've been given 2x squared plus 4x minus 2. So if they ask you to differentiate this in respect to x, all you're doing is you're assuming y is a subject. If y becomes a subject, then we are saying you're differentiating in respect to x, dy dx. So you multiply the power by the coefficient and then reduce the power by a 1. So 1 times 4 will be a 4. 1 minus 1 will be a 0. So, of course, the derivative of a constant is a 0. So that is basically our result. Now, in a case of implicit differentiation, we're actually trying to differentiate the implicit function. So what exactly is an implicit function? So if you look at the equation that I've written, this is implicit. Why? Because in this case, it is not possible for you to make y the subject of a formula. So it's very, very simple. So for example, if I can give you a normal function, an explicit function, where you have 2y minus 4x. If I ask you to differentiate this in respect to x, what are you going to do? You know it's possible for you to make y the subject, right? What do you do? So 2y is going to be 4x there, and then y becomes 2x. So now if you try to differentiate now, you'll find that the derivative of 2x is what? The answer is 2. Okay. Now, the idea of implicit differentiation is built on this very idea. So if you look at the 2y minus 4x, do you know what we can decide to differentiate it? I'll demonstrate how we go about the implicit differentiation. So we are trying to differentiate the entire equation in respect to x. Okay? So the moment you just differentiate something that has got nothing to do with x, you need to introduce dy dx. So y, for example, we'll differentiate it the normal way. Y is raised to the power 1 in that case. So 1 times 2 will be a 2. And then 1 minus 1. So as we said, the power reduces by 1. So you will notice that the y will basically go away. So you just remain with 2. Now, because we are differentiating y, we'll put dy dx. Why? Because we are differentiating in respect to x. And there in this part there is no x, so put dy dx. And then minus 4x. The derivative of minus 4x is a minus 4 equal to 0. So the idea of implicit differentiation is you need to make dy dx a subject. So therefore, if you add 4 both sides, this negative and the positive one will go. And then divide by 2 both sides, this 2 will go away. So you end up with the same result as in making where we had made y the subject, right? The answer is still a 2. So with that understanding, we are now capable of simplifying the question that is on top implicitly. Okay, so if you look at the first part, we have x squared. So what is x squared? If you differentiate that, what's the derivative? It's 2x squared. It's 2x, sorry. The power reduces by a 1. And then y squared, the same. It will be 2y. The power reduces by 1. Now, we are differentiating in respect to x. So I'll put dy dx. And that is the only rule that you need to remember. Always add dy dx in a case where you differentiate a letter that is not of our interest. Okay. And then minus 4x. The derivative of minus 4x is what? Is negative 4. The derivative of 5y is what? Is 5. Now we've differentiated y, so put dy dx again. That is the only thing that you need to remember. Very important. The derivative of a constant is always a 0, so we just remain with a 0 on the right hand side. Now at this point, we need to maintain that items that are having y on the left hand side. So we have 2y dy dx, and then we also have plus 5 dy dx. So every other term would have to go the other side. So we are remaining with 2x and minus 4. So we have 4 minus 2x. So we'd have to now, if we look at our left hand side, we'd have to factorize out the dy dx since we want to make it the subject. So after we do that, we have dy dx. In the brackets, you have 2y plus 5. On the right hand side, you have 4 minus 2x. So
we know what to do there. Our goal is to make dy dx a subject, right? So ultimately, you'd have to divide by this on both sides, so that you just remain with what? With it on the other side, so that it will be 2y plus 5. So what is our derivative of that implicit function? And that basically introduces the idea of implicit differentiation. Of course, just one more example to just help you understand one thing that is very necessary, very important in terms of the product rule, the way we tend to apply the product rule when we're dealing with implicit differentiation. Now, consider a situation where you have y squared and then multiplied by 2x. So in this case, how do you differentiate this implicitly? So the basic idea is this is now going to be considered to be a product rule. Okay, to be product rule. Product rule is the one that's going to apply. You can even add some more functions to just make it more interesting. Okay. So product rule demands us to consider first of all if any term of your choice. I'll start with y squared, and then I'll multiply by the derivative of the other. So the derivative of 2x is a 2 plus. So in the first part I considered y squared. Now I'll now consider 2x. I'll start with 2x. And then I'll multiply by the derivative of the other. So the derivative of the other is y squared in this case. So y squared, when you differentiate it, will be what? 2y. Now the fact that we're differentiating y instead of x, we'd have to put dy dx. That is the only rule. Whenever you differentiate a term adding y, add dy dx. Okay, so everything else remains the same. The derivative of y squared is what? It's 2y. Now because it's y, we're putting dy dx because we are differentiating in respect to x. The derivative of 2x is just a normal, it's a 2. Okay, so now at this point again, the same rules apply. You need to remain with what? The term having dy dx on the left hand side. So I'll expand this term. So you will notice that 2x times 2y will be 4xy, and then we have a dy dx. The other term having dy dx is 2y dy dx. Everything else goes the other side. So we have this part to be negative 2y squared, and then the constant 2 also goes the other side. Okay, so at the point where we've reached now, all we can just do is the same procedure. Just factorize the dy dx, right, on the left hand side. So we have dy dx. What remains? 4xy for the first part, and the other part will remain with 2y. On the other side, we have negative 2y squared minus 1. So to make things easier, we'll divide by this both sides, so that we just remain with 4xy plus 2y. And that basically summarizes the idea of implicit differentiation. If you've understood whatever we've done, I believe you're okay. So make sure you subscribe to have access to more other videos related to math, chemistry, physics, and biology. Okay, let's just try to understand how we get to apply implicit differentiation to exponential functions. Okay, so if you look at this case, we have this is our function, and then of course we want to determine the derivative, of course, in respect to x, dy dx, y respect to x. Okay, so we know the basic standard of differentiating a function. Some of the basic things that I would have to remind you is if you're differentiating a term x to the power 3, all you just have to do is multiply the power by the coefficient. Okay, so there's a 1 there, 3 by a 1 gives us a 3, and then the power would have to reduce by a 1, so it becomes 2. That's how we differentiate the normal functions. Okay, now I would have also to remind you to say if you have a constant, constants of course becomes zeros, and then of course let me talk about the exponentials. So if you have e to the power x, its derivative is what? Multiply the original function by the derivative of a power. So you agree with me that the derivative of x is 1, so the derivative remains the same. Now the moment I put, let's say, let me put 2x, Now I'm saying the derivative of an exponential function is multiply 2, right? So multiply the derivative of a power to the original function. So the derivative of 2x is 2. So we have 2e to the power 2x. So that is how we differentiate the exponential functions. Now, with the understanding of the basic differentiation and of course the exponentials, we can straight away go and deal with our question. Now, if you are new to implicit differentiation, I would advise you to watch a video, okay, with a tag on top, and also the link is provided in the description. You can watch that video on implicit differentiation. Okay, so just to give you a background, if you have 2x y squared, okay, plus, I can add something else, let's say x squared, and then I say 3y cubed. You know, if you get to observe this case, you want to differentiate the function in respect to x, dy dx, of course, and then you cannot make y the subject. We call that implicit. You can't make something the subject, okay? So that's what we're trying to talk about in this case. So how do we differentiate it in case where we have an exponential function? Okay, so having an exponential function as we are given in this case, it is going to be very simple. So I know this is easier, that is easier. I'll focus more on the middle part first of all. We try to work out, which is e, right? So we have e to the power x to the power 3, y to the power 3, okay? So I emphasize to say the derivative of an exponential function with a base e, just multiply the derivative of the power to the original function. So I just have to multiply the derivative of what? So the derivative of the power, which in this case is x3, y to the power 3, and then against the function itself, which is e, x to the power 3, y to the power 3, right? Okay, so we need to find the derivative of this. Okay, so we have a product of two different things. Okay, so how do we handle that? So this requires you to understand the product rule. If you've not, and if you don't know about product rule, you can also watch a video provided in the link. The link is in the description. Okay, so product rule tells us to say that if you have two functions multiplying, in this case we have got x to the power 3 and y to the power 3. I'll not write any formula here, I'll just go direct. So you can get any term to be the first term to start with. In this case, I'll start with x to the power, I'll start with y to the power 3. And then I would have to multiply it against the derivative of the other part. So what is the derivative of x to the power 3? So I explained how to differentiate the functions, right? It's going to be 3x to the power 2. The power reduces by 1. The power multiplies the coefficient. Okay? Plus. So that's the product rule. Now, in the first part, we had started with y to the power 3. In this case, we're going to start with x to the power 3. And then multiply the derivative of what? The other part. So the other part in this case is y to the power 3. So if you differentiate y to the power 3, ignoring the fact that it's a y, you get 3y what? Squared. Now the fact that it is y and we are differentiating in respect to x, would have to add dy dx. Okay, so simplifying all this, what do we remain with? So we'll have 3x squared y to the power 3 plus. So there equally we can say we have 3y squared x to the power 3 dy dx, right? Okay. So I can allow me to erase and create just some space there. Okay, at this point where we are, we've determined derivative of this guy, which is our power, right? So we can just quickly substitute in. Okay, so I'll go back to the original function. So dy dx. So of course, yeah. Okay, there's a 0 there. It's got to 0. So what is the derivative of x to the power 3? We talked about the derivative. It's what? 3x to the power 2. The power reduces by 1. Of course, the power first of all multiplies the coefficient 1. Now, the middle part, I said when differentiating exponential functions, you just have to differentiate the power. So the derivative of a power is exactly what we have on the bottom there. If you differentiate x to the power 3, y to the power 3. So we have 3x squared, y to the power 3, plus 3y squared, x to the power 3, dy dx. Now, you'd have to multiply everything there. Multiply by what? The original function itself, which is e to the power x to the power 3, y to the power 3. That's how you differentiate exponential functions. And then the derivative of a constant is just a 0. Okay, ultimately, this is what remains. Now, whenever we're dealing with implicit differentiation, after you perform the differentiation, you'd have to make dy dx to be the subject of a function or expression that you get to have. So remember, we have got a function multiplying everything in the brackets, right? So we can basically get to expand. So we have 3x squared plus 3x squared y to the power 3, which is like the first term, multiplied by e, which is now coming from outside, and then again plus 3y squared x cubed times dy dx, and then now also times ex to the power 3 y to the power 3 equal to 0. So our goal is to make the part with dy dx a subject. So everything else goes the other side. So we remain with 3y squared x cubed dy dx, and then we have e to the power x to the power 3 y to the power 3 is equal to. So these two terms are going to the other side. They'll become negative, right? So we have negative 3x squared, negative 3x squared y cubed exponential x to the power 3 y to the power 3. Okay, so at this other point where we've moved now, it becomes easy to simplify it because we've almost made dy dx the subject. So all we just have to do is divide by this part and that part. Okay, so after doing that, what do we expect to have? So we can say our dy dx is going to be the left part, which is negative 3x squared minus 3x squared y cubed x to the power 3 y to the power 3, and then we are dividing by what? This 3y squared x cubed, and then exponential x to the power 3 y to the power 3. Okay, so at this very point we've made dy dx to be the subject of the formula. So we've differentiated using the implicit differentiation. And then just one more question to make sure that everything we've done is stuck. Okay, so this is the second practice question. So we have 5y squared plus 2x plus e to the power 3xy. How do we get to differentiate this? Okay, so implicit differentiation, I'll go direct. 5y squared, that will give us 10. 2 times 5 is 10. The power reduces by 1, it will be y to the power 1. So the fact that we're differentiating in respect to x, y in respect to x, would have to multiply by dy dx. Plus, so 2x, this is just we're differentiating x, which we're interested in, to just be a 2. And then the other part where we have exponential. So I said when you're dealing with exponential, you'd have to first of all determine the derivative of the power. In this case, the power is 3xy. So we have products of two functions. Okay, we can say we have 3x and also y. So what is the derivative of 3x? It is a 3. And then what is the derivative of, we'd have to multiply by the other part, which is just y. Plus, what's the derivative of y? So the derivative of y, the power 1 is just going to give us 1 times dy dx. Why am I saying multiply by dy dx? Because we are differentiating y. So it's dy dx. And then once we multiply by the other part, which was 3x, right? It's that simple. So this is product rule. So the derivative that we have gotten, we're therefore supposed to multiply it against the original exponential function. So the original exponential function is e to the power 3xy. So at this point where we have reached, we are now at liberty of trying to make dy dx a subject. Before we could get to do that, we'd have to expand the other term. So we have 10y dy dx plus 2. So we have 3y multiplying by the exponential function to be 3y. So of our exponential function. And then this part as well, 3x multiplied by the exponential. And then of course not forgetting our dy dx equal to 0. So if you try to look at what we have, our main parts are having the dy dx. Those are the two parts, right? So those ones are going to remain on the left hand side. So obviously we have, I can directly factorize dy dx without wasting much of your time. So dy dx, and then remaining, the first term is 10y, and then the other one is 3x exponential 3xy equal to, what is going the other side are just these two terms. So I have minus 2 minus 3y e 3x to the power y, or e to the power 3xy. So at the point where we've reached, we can just divide both sides. So ultimately we're just going to remain with 10y plus 3x e to the power 3xy. So that is basically how simple it is to determine the derivative of exponentials using implicit differentiation. Okay, so just like I said, if you want to understand more how we go about the implicit differentiation, check out the video in the description, and also understand more about the product rule to make things easier. I do get to deal with this concept. So thank you very much for taking some time to watch this video.
The journey under calculus is becoming more interesting and interesting. So we've already talked about differential calculus. Let's try to talk about the tangents and the normal lines. So I'll actually explain this and then just look at two questions to help us solidify whatever we're going to talk about. Considering this curve of ours, taking that to be our x or y plane, okay? So considering a certain point on the curve, so there are two lines there. There's one line that will cut the curve at a single point, and then there will be a line which will be perpendicular to that point. So the line perpendicular is called the normal, and the line parallel is called the tangent. Now coordinate geometry is very important. So when you talked about the linear equations, you understand that when two lines are parallel, it means their steepness is the same. In other terms, the gradient of two parallel lines are equal. And then for the perpendicular ones, so that's if I introduce a line perpendicular, meaning that they make an angle of 90 degrees, and taking that to be M3, their product M1 and M3 is equal to a negative 1. That's very important. So with that understanding, we understand that the gradient of a curve at a given point is going to be equal to the gradient of a tangent. So taking the gradient of the curve at that point to be m, and then that of a tangent to be m1. That is a relationship there. And then for the normal and the curve, their product is a negative. In other terms, m is going to be -1 over the gradient of the normal. So that relationship is also very important. And I think that's what all you need to know. But the other thing under calculus is the derivative. That's if you have, for example, an equation y is equal to x squared, and then you try to determine the gradient function of the derivative, your dy dx is going to be equal to 2x. So you understand from the introduction where we talked about first principle, I did emphasize to say this is called the gradient function, meaning that it can help you find the gradient of the curve or any function at any given point. So given the value of x at a certain point, I'm able to find the gradient. Okay, so now I'll be using this relationship now to help us find the equation of the tangent and the normal to the curve at any given point, just using the derivative and then the x coordinate given. Okay, so let's look at an example to just understand what I'm talking about. Considering a case where our y is equal to x squared, that's our equation, the coordinate to be 3, 9. Okay, so we need to find, let's try to find the tangent to this curve at this given point, tangent and the normal. So I'll find for the tangent and then you will find for the normal. So let me try to show you how. So the first thing that we'd want to do is first of all try to find the dy dx. Derivative is 2x. Okay, so that is called the gradient function. Now we can find the actual gradient at the given point. In this case, our value of x is 3. So if you substitute our 3, we'll get 6. So this is our gradient of a curve at the given point. So of course, it doesn't matter whether you know how to sketch the function or not, but I believe this one is easy to sketch. This is a function that's like this. It doesn't go to the negative part like that. So taking 3, 9 is somewhere here. 3 and then comma 9. So we're trying to find this tangent and then also the normal. So starting with a tangent is a line that cuts the curve at a single point. In this case, the point is 3, 9. Now, what did we say? Now, I did say that the tangent and the curve at a given point, their gradients are equal. So the gradient that we've determined, which is of a curve, is basically also equal to the gradient of a tangent at that very point. So meaning that we have our gradient to be 6. Now tangents and normals are lines. So if you have the gradient and then you have the coordinate 3, 9, you should be able to find the equation. How? So you know of this, I believe, y is equal to mx plus, which is the form of a standard linear equation. So plugging in so that we find the constancy, this is our y is 9, our gradient is 6, our x is 3, so 9, and then 6 times 3 is like -18, which is equal to c. So c is equal to -9. So you found your c. So the equation becomes y is equal to, the gradient is 6, so you have 6x, and then your c is 9, so -9. So this is the equation of the tangent to the curve at that given point. Okay, so how would you handle it for the normal? So for the normal, the product of the gradient of the normal line, or the normal to the curve at a given point, the product of its gradient with the gradient of the curve, which in this case is 6, their product is equal to -1, meaning that for our normal is going to be -1 over the given gradient, and that is always the case. It is -1 given the gradient of the normal is -1 over the gradient of the curve. So you found this. Now we have our coordinate to be 3, 9. That's a point where the normal cuts the curve. So using this and applying the same principle, find the constant c and then just write the equation. Simple to deal with, right? Now, to just make it more interesting, look at a more advanced question, which is very nice. Okay, so pay particular attention to this equation, to this question, that is. The curve C. So we have a curve C, take note, as an equation that, so I'll rewrite the equation. The equation is 2x cubed plus x squared minus 3x minus 7. That's our equation. Now the point P with the x coordinate, negative 0.5. So if I were you, I need to find the y coordinate in advance because I know it's going to ant me as I proceed. So how do you find the y coordinate? The y coordinate uses the equation of the curve. You know that it is equal to y is equal to that. So plug in the value of 0.5 at every point. Okay. So after plugging in the value I'm getting here is negative 8. Hopefully my calculations are okay. So we have that point P. Now read the question again. The curve C as that equation. The point P with the x coordinate at 0.5 lies on C. So to just help you understand, I can come up with a simple sketch. We can take that as our curve, and then we can have a point. So we have a certain point, negative 0.5. So let's say somewhere there. Let's take that to be our coordinate, negative 0.5, negative 0.5, comma negative 8, which we've already found. So now, this is a point P. So the point P with x coordinate lies on C. So this curve is called C. And then what else are we told? The tangent to C. So the tangent to C. So we have a tangent at that point at P is parallel. So that's this tangent. So that's the tangent to the curve C at the point P. That tangent is now parallel to a straight line. So there's another straight line. Okay, I can just put it down. So this line is parallel to the tangent. Now this line, the equation has been given to be what? The equation has been given to be 2y minus 3x plus 4 is equal to 0. Okay, so find the equation of a tangent at P in the form that. So we just need to find the equation of a tangent. Now the beauty in this case is, if we look at what we have, it's somehow it's somehow simple and straightforward. I don't see the point. I don't see the reason why they gave us this tangent though. I don't see a reason. Maybe we understand as we try to proceed because I feel the information given about the curve is important, is necessary and sufficient to find. Let's try to look at it. So the curve C, the equation has been given to be this part. Okay. So I believe we're able to find the gradient from there. And then the coordinate is already there. So I don't see the point. Anyway, let's try it out. So dy dx becomes, if you differentiate this, you're going to have 8x squared plus 2x minus 3. Now we can plug in the negative 0.5, which I believe is the negative 0.5. Was I even correct there? I think there's something, I made a mistake somewhere when finding the coordinate of the y coordinate. So anyway, the value of x is negative 0.5 according to the question. So 0.5 is the same as half. So 8 multiplied by, where there's x, we'll put negative half. So negative half squared is 1 over 4. And then here we have a negative half again, minus 3. So there we're going to have a 2 minus 1 minus 3. 2 minus 1 is what? Is a 1 minus 3, negative 2. So our answer is negative 2. So that is the gradient of that curve at that point. So m is equal to negative 2. So we can just find the y coordinate correctly to help us find find what? To help us find the equation of a tangent at P. What else do we need to know? So let me try to review finding the y coordinate there. So we have 2. Now whenever you raise a negative number to an odd power, it will be a negative. So we're going to have negative 1 over 8. And then when you raise negative 1 over 2 to the power 2, it will be positive 1 over 4. And then minus 3, negative 1 over 2, minus 7. So at this point, we have negative 1 over 4 for the first part, plus 1 over 4, which I believe is a 0, and then plus 3 over 2, minus 7. So if we do multiply there, 2 times 7 is 14, and then you have got a 2 on the denominator. 3 minus 14 is negative 11, I believe. So negative 11 over 2, that is our y coordinate, I believe, if everything is correct there. So negative 11 over 2. So at this point, I think I can leave you. The gradient is negative 2. The coordinate has been given. You're able to use this format to find the. So this is why I was saying I didn't see the point of them giving us the line parallel to that. But let me try to look at it if it's going to add up. So let's try to make y the subject in this case. So 2y becomes equal to 3x minus 4. And then divide by 2 throughout. Y becomes 3 over 2x minus 2. So our gradient according to this equation is supposed to be 3 over 2. So if you are basing your calculations on the line parallel to it, this is supposed to be the gradient. So I expected them to be the same because I'll read the question again. The curve C has equation that the point P with x coordinate lies on C, okay, and the tangent to C at P is parallel to a straight line that. Find the equation of the tangent at P in the form of that. So anyway, based on the question, but in the actual sense, that's why I was saying it wasn't necessary, but I feel they wanted us to focus on the usage of the parallel line to help us find the equation. So all we can basically do is the thing that is very important is to note that the gradient of that line is equal to the gradient of the line which is the line to which it is parallel to. I think that's the most important point, the takeaway point. So even in a case where the where the equation is not given, if the equation is not given, you should be able to arrange the formula in the form of y is equal to mx plus c and get m as a gradient of this other line and then use it for the other line. But I feel what they needed to give you again is they would have to give you the y coordinate. Okay, so in this case, take your gradient to be 3 over 2, which is coming from the line parallel to the tangent, and then get the coordinate negative 0.5 comma negative 11 over 2 and try to find the equation. Okay, so this is where we end for this tutorial. I hope you understand how to find the normals and also the tangents to the curve and being able to apply them in different questions that may come as complicated. Let's talk about the concept of increasing and decreasing functions. So this is under differential calculus. Okay, so we already know how to determine the derivative of a function. So the derivative of a function can tell you whether a function is increasing or decreasing. But before we look at how, let's try to understand what it means for a function to be increasing or decreasing. Okay, so consider a linear function like this, and then consider another linear function from the other direction like that. So which one would you say is increasing and which one would you say is increasing? So we basically get to observe that by looking at the x-axis. So if you look at our x-axis, let's take this one to be maybe somewhere negative 4 and then this side positive 4. So the question that you need to ask yourself as you are moving from the negative x-axis towards the positive, what is happening to the y value. So obviously you can actually note that for this other one, as we move towards the right, the value in y, there's what? We can observe or note an increase in the value of y. In other terms, the function is increasing. But for the other one, where the value of y is kind of decreasing, we can see that there is a decrease in the function value. Okay, so this is basically what we're trying to say. Now, of course, if you try to look at the equations of these linear functions, it's an undeniable fact that if you try to determine the equation, likely the equation is supposed to be in that form for that other one, and then this one as well. Okay, so explicitly mentioning that for this other one, m is of a steepness is expected to be a negative, the other one positive. Okay, now we've also talked about the derivatives to say the derivative of a function can help you determine what? The gradient. We call it derivative function or the gradient function. Okay, so I think you've now gotten the point there. So you know what it means for a function to be increasing, and you now know what it means for a function to be decreasing. Now, of course, calculus is more concerned or interested in talking about curves that make it more interesting. So let's look at the curves and just basically see what we might expect. Okay, sorry for that. So if you talk about an exponential function, we know that an exponential function behaves in this way, like that. Okay, so you can see that as we move from the negative x-axis towards the positive part, the value of y is doing what? Is increasing. So that's an example of an increasing function. So that is of course e to the power x. Now of course we can also have another example of the logarithm function as well, something like this. So that is also another function. You can also see now that it's also what? The value of y is increasing as we move from the negative or from left to right. We can see an increase in the value of y. So that is also an increasing function. Okay. So examples of decreasing functions would be the ones where it's like going down as you move from the left to the right. Okay. It can be like this as well. The value of y is reducing as you move from left to right. That's what differentiates decreasing and increasing functions. Now, these are kind of perfect functions that we've talked about so far. Now, there are also some functions where it's mixed up. Depending on the range that you're talking about, the function behaves differently at different domains. So you can see clearly to say if we try to observe this function at this range, at this domain, we've seen that it's increasing by that line. Here you can see that it's decreasing, continues to decrease there, and then again it starts to increase. So it depends on the kind of functions that you're talking about. So the domain also does matter. So now this is where we're going to be working with the critical points and stationary points to help us determine for certain functions where it is increasing and where it is decreasing. But of course, we've understood what it means for a function to increase or decrease. So I think this is going to be more interesting as we talk about curve sketching. That's why you understand to say, okay, a function can be increasing, decreasing, and be constant at given points. Okay, so theoretically talking, before we even head to curve sketching, let's look at a few functions and try to check whether they are increasing or decreasing functions in general. Let's consider a function y is equal to x squared. So this is a very common function. So even before we apply calculus, let's try to sketch it. So obviously you know that this is squared, so you don't expect to get any negative at any given any value of x. So this is how the graph is going to be. Okay, so of course one statement that you can notice, you can clearly see that as we move from left to the right before 0, what are we saying? The function, the value of y has reduced. So considering that domain, so from the negative infinity all the way up to 0, we can basically see that the function is what? The function is decreasing. And then after this, what can we see? So from 0 again increasing, so from 0 all the way up to positive infinity, we can conclude to say the function is now increasing. Okay, so with calculus, what you need to understand is when the derivative or dy dx is greater than 0, when it's greater than 0, or when you have a positive value in other terms, then you need to conclude that the function is increasing. In a case where it is less than 0, in such a case you conclude that what? The function is decreasing on that interval. Okay, so of course there are some cases where the dy dx will just be equal to 0, but we'll talk about that. For now, take it as greater than or equal to 0 to be an increasing function. Okay, a case where it is equal to 0 will make sense a bit later. Okay, let's move on to a different kind of a function where we have, let's change the power, let's make it the power 3. So this one is a bit unique compared to, since this one can accommodate both positive values. So when you're on the positive part, values will continue to be positive. Then as we go to the negatives, it will be negative values alone. So its function behaves like this, and then again behaves like this. So I actually didn't finish on the y is equal to x squared. So y is equal to x squared, if you differentiate it or determine the derivative, our dy dx is equal to 2x. So if you consider the part, of course the graph is something like this, okay? I hope you've not forgotten. For x squared, the graph is never cuts the negative part of the y-axis. Okay, so if you consider values less than 0 going this side, you can get a negative 1. You plug in the dy dx there. So if you plug in there, what do you expect? If you plug in a negative 1, the value will be a negative 2. So a negative value, remember I said when the dy dx is less than 0, then the function is decreasing. So we can clearly see that it's decreasing. Of course, if you get the positive part, you expect that it will give you as a positive value, which indicates that the function was increasing. Now, of course, I can now mention that if a dy dx is equal to 0, that is referred to as a critical point or stationary point. You understand what stationary points are? So stationary because the function is neither increasing or decreasing at that given point. Okay, so you understand. So y is equal to x to the power 3. If you look at what I've drawn here, what you might expect is after 0 going this side, positive from 0 to positive numbers, we can see that the function is increasing. As we move from the left again, we can still see that the value of y is still what? Is still increasing. So how do we tell? How do we know? So let's try to differentiate this function. So according to what we've looked at, we've seen that the function is purely increasing throughout. So dy dx, hopefully to confirm that, if you differentiate this function, we're going to have 3x squared. Now this is where it becomes interesting. Whenever you've got x or any variable raised to a positive even number, or let me just say positive power, not necessarily positive power, but an even power, 2, 4, 6, 8, and so on and so forth. In such a case, you can never get a negative, not unless if you have a negative coefficient. But in this case, it is just like that, 3x squared. So the values that you're going to plug in, whenever you plug in a negative where there is x, they'll continue giving you positive values. So even if you get the values less than 0, negative what, you raise with the power 2, it will become a positive. So here all values will always be positive, which clearly proves that this function will be increasing throughout. Okay, I think that's very cardinal and very important to just help you understand. Okay, so with linear functions, of course, it becomes very easy because you know you can just write it in the form of y is equal to mx plus c. So if you make y the subject here, you would have to divide by 4 throughout. So y is equal to, of course, take the other part to the other side, and then you have plus 7. So you can clearly see to say the gradient m there is a negative. So this is expected to be a linear function that is what? Decreasing. Even if you try to differentiate this part, y prime or the dy dx is just going to be negative 3 over 4. So a negative value indicates the function is decreasing. Okay. And what about if you have certain interesting parts? What if you had f of x and then raised to the power negative x? I'm so curious to just try to understand how you would look at this. Would you say this function is an increasing function, a decreasing function, or what would you say? So let's try to determine the derivative. So you can not easily sketch this function, so let's try to determine the derivative. Now of course we understand we apply the would have to apply the product rule. We've got two different functions here. So I'll take the first one, x, I'll differentiate it, I'll get a 1, and then I'll multiply by the original other part, and then I'll start now by the derivative of e to the power negative x. So we said, how do you differentiate exponentials? So a derivative of an exponential, differentiate the power. So a power there, if you differentiate, you get a negative 1. So now negative 1 multiplied by the original itself. That's the derivative of an exponential function. Okay. Of course, you have to add the natural log of what? Natural log of the base itself, which in this case will just cancel out, and then multiply by now the original first part. So at this point, you can factorize e to the power negative x, which I believe is common. For the first part, you remain with a 1, the other part you remain with a negative, and then x. This is the derivative that you have. Okay. So one thing that you know is an exponential function, if you try to sketch it, it never cuts the x-axis. This is the way it behaves. It will always be getting closer and closer to x as you move towards the negative numbers, and will increase exponentially like that. So meaning that no matter what value of x you put there, the function is expected to never go to the negative values. Okay. Of course, a counterpart, natural log, behaves like this. Okay, that's why they're inverses. So in this case, what do we expect? So meaning that what is determining the sign or or any outcome of this function is purely what is in the brackets, which is 1 minus x. So we understand that if you get values of x that are less than 1, or values of x that are less than 1, all you're going to be getting is, so if you have x being less than 1, values that you're going to get will remain positives. And then if you get a value of x that is greater than 1, you will now begin getting negatives. For example, if you put a 2 there, you get what? You get a negative, right? Yes. So in a case where we're getting a negative where x is greater than 1, we can clearly indicate that within that domain, the function is said to be decreasing. And then in a case where the values of x are less than 1, we'll always get positive. So the function is now increasing in such a case. Remember, always from what is outside, you always be getting a positive. So what will determine the overall sign is what comes out from the brackets there. Okay, that's how you can look at such a function. Okay. So of course, I've mentioned we can also have cases where you have now a function which is, I think we've already encountered this. Yeah, we've already encountered this. But of course, let's try to look at this quadratic function. Let's try to differentiate it. So y prime will be 2x plus 4. So for this function, now this is where it becomes interesting, because how do you basically know or tell when we expect this function to be increasing or decreasing? So let's try by guessing first of all, and then I'll show you the simpler way of undoing it. So by guessing, when do we expect the what? When do we expect the dy dx of the y prime to be positive, and when do we expect it to be negative? Okay, so clearly, if I put a 2 there, or if I put a negative 2, I expect this is going to give me 0, right? Yes. So it's like negative 2 is like the deciding point, because that's why it's equal to 0. So what if I try to get a value greater than negative 2? Maybe a 0, a 1, a 2, and so on and so forth. So in such a case, if I get, for example, a 2, I put it there, I'll get a positive result. So going this side, I'm getting a positive result. If I go below negative 2, for example, negative 3 times 2 gives me negative 6 plus 4, which is a negative. So going this side, I'm getting a negative. So I would guess to say, okay, well, each time my value of x is less than negative 2, what am I getting? I'm getting a function that is decreasing. And then each time my value of x is greater than negative 2, what am I getting? An increasing behavior. So that's by guesswork. Now, the simpler way of trying to approach this is where we introduce in what we now call the critical point. So the critical point is where you expect that the dy dx will be equal to 0. So 2x plus 4 becomes so equate whatever you've determined as your dy dx, equate it to 0. So 2x is equal to 4, negative 4. So x becomes negative 2. So that is always very important. So of course, we'll look at cubic functions and other bigger functions where you are going to have more than a single critical point. And that is very necessary for you to determine the parts where the function is expected to increase or decrease. So if you have a critical point like this one, all you just have to do is try to now determine the behavior on the left and the positive side, of which we've already determined that. Of course, after, when you go to the side where it is less than negative 2, it's decreasing, increasing on the other end. Now, there will be interesting parts now where we have a curve like that. So such a curve is going to have critical points at that point, at that point, that point. So the way you basically get to look at this is, for example, you'd get this value of x there, maybe negative 4, and then 1. And then, of course, this is going to be done theoretically because it will not obviously be sketched. So you'd have to look at negative 4 and 1, and then you get any value, plug in the derivative function. If it obviously you expect that here to give you a positive value, here to give you a negative value. Okay, it will continue negative value and then positive value. So of course, there are points where now at these points now these points where which we are going to talk about are called stationary points, where now even the dy dx will be equal to 0. Okay, point like that one. Okay, so you understand. But for now, understand that we'll be using or determining what we are calling critical points to help us determine where parts of the function of a curve, where it is increasing or decreasing. And I think that is one of the key concepts that helps us to sketch a curve. Okay, let's proceed now and just get to look at the stationary and the critical points. Let's talk about the stationary and critical points. So it's very interesting, actually. I think I've never given it a thought, not until I was thinking about making this video about that. So actually, I've always known that when it comes to determining the critical points or stationary points, it's of course a point where we expect that the dy dx is equal to 0. Well, while there's nothing wrong with that, I didn't understand where the word stationary came from. So let's consider this graph. Maybe let me draw it more carefully so that you can see certain points that I want to be visible. I'll draw a first part of the graph like that. Maybe let me end it like, okay, and then I'll begin it like this. Okay. So I think that's what I want. So when you look at this graph, this part is increasing, that part is decreasing, this part is increasing, this part is reducing. Okay, so there's what we call increasing at a reducing rate and all that. We talk about it as we move. So this is increasing at a decreasing rate, this part increasing at a decreasing rate because we are reaching at a maximum, so it's increasing at a decreasing rate. And then this is increasing at an increasing rate. Okay, so a basic idea is if I give you examples of an exponential function which increases at an increasing rate, and then also a natural log which increases at a decreasing rate, it's more like this. So it's not as increasing as fast, but it's increasing. So increasing at a decreasing rate, and then this is increasing at an increasing rate. Okay, just know that for now. That is also that. So I've already mentioned to say this part you can see the graph is increasing or reducing, and then this part is still reducing. Okay, so don't worry about that for now. So if you look at this point, we draw a tangent there, and then you can draw a tangent there. So these points where the dy dx is equal to 0, or where the tangents to the curve are parallel to the x-axis, if you want in other terms, but what you need to understand is at that point dy dx is equal to 0. So at that point the graph is said to be constant. It is neither decreasing nor increasing. So we call it a stationary point. Stationary because the function is neither increasing nor decreasing. So it's like stationary. Stationary means no change. Okay, so at that point, so at these points where dy dx is equal to 0, we refer to as stationary points because the dy dx is equal to 0, or in other terms, the function is neither increasing nor decreasing. Okay. Now, not only do we have that point, we also have the point where the decreasing parts are meeting, one from the minimum point, the other one from the maximum point. So where there's that change of behavior. So more accurately, what happens is this part is coming from the maximum part like this, and then another part going to the minima comes to join. So there's this part, which is of course decreasing at a decreasing rate, and then there's this part decreasing at approaching the minima. So at this point where there is that change, you can see there's more like a curve, okay, like this, like this, and then that's what done. Anyway, this is what I'm trying to talk about. The point where that occurs is called a point of inversion. So even at that point, the dy dx is equal to 0. Okay, so a point of inversion. So a function is never maximum nor minimum at that point, but dy dx. So when dy dx is equal to 0, and then the point is neither a maxima nor a minima point, the point is called a point of inversion. So of course, we'll look at the second derivative. So the second derivative is what helps us to determine whether a point is a maxima or a minima. So of course, when the second derivative when the second derivative is greater than 0, or in other terms positive, the point is said to be a minima. When the second derivative is less than 0, meaning that it's negative, it is a maxima. But of course, in a case where it is equal to 0, that's now what we call a point of inversion. So stationary points are points where the dy dx of the derivative is equal to 0. And we've got 3 examples of stationary points: maxima, minima, and the point of inversion. Okay. Now, what are critical points? So what you need to understand is the stationary points we've talked about are critical points. Okay. So a critical point is, these are points where the dy dx is equal to 0, or the function does not exist, or equivalent we can say, or the derivative does not exist at that point. So meaning that a critical points is a bigger set consisting of stationary points as well. I can give you an example of such a curve. So we can take this the same normal kind of a curve. Okay, so of course I believe you've talked about certain points that may be undefined. Okay, but of course, being more realistic, which usually happens in most of the cases where you approach 0, maybe at the point where x is equal to 0, usually undefined, but it can be at any point. Okay, so that would be in a case where on the denominator, for example, you just have x, and then you have a certain function on top, something like that. So a case where x is like equal to 0, at that point you expect that the function is not defined. This may be a derivative or just a function itself. So at that point is actually a point you can refer to as, it can still be called a critical point. So this may even be at the minima or maxima, it will be a critical point. So what makes it different is that stationary points are restricted to a part where dy dx is equal to 0. In a case where the derivative of a function is undefined, those are still referred to as critical points. So critical points is a bigger set, broader, as compared to the stationary points. And I think this is the key difference that most students get to miss. Now let's look at a few practice questions that will just help us solidify whatever we've talked about. So consider a case where f of x is equal to x to the power 3 minus 3x squared minus 9x plus 5. So find all the critical points of that function. How would you do it? So of course we expect to differentiate the function. So we're going to have 3x squared minus 6x minus 9. So that is our derivative function. So for us, how do we find the critical points? So we've said the critical points, of course, whether they stay critical points or stationary points, this you expect that the intersection part is where the dy dx is expected to be equal to 0. So equate the derivative function to a 0 and then try to find the value of x. Now you can clearly see that this is now what? That is now a quadratic function that you can easily look at. So if 3 is common, you can factorize it to make it simpler, so that we can remain with what? X squared minus 2x minus 3 equal to 0. And then we can factorize what is inside, of course. So if we do factorize what is inside there, we're going to have x plus 1, x minus 3 equal to 0, which can easily help us find the values of x. So x is equal to negative 1, and then x is equal to positive 3. You can solve that using any formula you want, either by factorization as I've done it, by formula, or by completing the square. So the critical points can be found by, you'd have to find the y values. So you found the x values, so negative 1 comma something, 3 comma something. So what you're going to put there is, now for you to get the y value, you need to go back to the original function, plug in the value of what? Plug in the value of the x that you found. So for negative 1, if you plug in negative 1 to the power 3 is negative 1, and then that is minus 3, positive 9 plus 5. 9 plus 5 is 14. 14 minus 4, I believe that gives us a 10. And then all the same, if you plug in a 3 there, you get a negative 22. So that's how you find the stationary or the critical points given a simple curve like that one. Let's take it a bit more interesting and then get to look at something more advanced like that. You look at an exponential function. So of course, we've said for you to handle any of these, you need to first of all look at what? You need to look at the issue of finding the derivative function. So f of inverse of t is going to be equal to, how do you differentiate an exponential function? So multiply by the derivative of the power, natural log of a base. So in this case, the derivative of negative 3t is negative 3, and then we multiply the origin of function itself, and then natural log of a base, which is just natural log of v in this case. So that means that will disappear. I'm trying to mention that because you may have a case where you have 2x. How do you differentiate that? Derivative is derivative of the power, which is a 1. Maybe if I put it to the power 3x, the derivative of the power is 3, multiplied by the original part, and then natural log of 2. Now for e, natural log of e is just the 1. So that's what we have, and then the derivative of 2t is just a 2. So at that point, we've differentiated the function. Now for us to determine the critical points, we need to equate this to 0, right? Plus 2 is equal to 0. So how do you basically get to such a point where this is going to be equal to 0? So obviously, we can take the constant the other side, negative e, negative 3t plus equal to becomes negative 2 the other side. And then of course, if you divide by the negative of 3 both sides, e, what are we going to have? We're going to have 3e, or e to the power negative 3t is equal to 2 over 3. So how do we get to find the value of t? What's the best way for us to find the value of that? So the way we would handle that is by introducing the natural log on both sides, since we know that it is basically the inverse of e. So you are going to have negative 3t is equal to natural log of 2 over 3. So natural log of 2 over 3 is something that you can actually simplify using a calculator. So of course, you can divide again by negative 3 both sides. So you're going to have negative 1 over 3 and then natural log of 3 over 2. So you can simplify that on the calculator. So what you're going to find there is a value of t, which is more like the value of x, and then to find the value of y, you'd have to go back the function and substitute there. Yeah, that's how we are going to find the critical point. I just needed to mention that of course it's not as complicated as it sounds. Okay, so no matter what you're given, if you want to find the critical points, all you just have to do is equate the derivative function to 0. So let's consider now one more interesting form of the function that I would want us to look at. So what if f of x is equal to x and then raised to the power 2 over 3. Feel free to just pause the video and just try to determine the critical points. The derivative becomes 2 over 3, and then x, reduce the power by 1, so 2 over 3 minus a 1, that's going to be what? Negative 1 over 3. Now some of you know that if you've got x raised to the negative power, you can just take it the bottom, so that you have 2 over 3x and then raise to the positive power of 1 over 3. Okay, so how do you find the critical points of this function? So of course we've already established to say you get to find the critical points where the derivative is equal to 0. Now you notice one thing about this is if you have got 2 over 3x raised to the power 1 over 3, this can never be equal to 0. No matter what you're going to do, it can never be equal to 0, meaning that in this case you don't have what? Stationary points. No stationary points. But of course you know that if you plug in a value of 0 there, x becomes 0. This whole thing becomes undefined, right? So now where the function is undefined, that is referred to as what? A critical point. Okay, so a critical point is where the derivative of a function is undefined. In this case, this is the derivative, so the derivative is undefined when x is equal to 0. So it's the critical point becomes 0 comma, you find the y coordinate by going back to the original function, which is 0 raised to a certain power, which is 2, 0. So that is a critical point. So this is what differentiates now the critical points from the stationary points clearly with such an example. So for the sake of your practice, I want you to just try out these two interesting questions. Consider a case where y is equal to x e to the power negative 3x. Determine the critical points. And then one more would be x plus 1 over x. Determine the critical points.